want to welcome you to another beautiful week. Before I get started today, of course, tomorrow I'm actually going to publish midterm one result as I'm going to finish grading today. Okay, so today's topic was centered on small sample confidence interval. Initially, I wanted to start chapter 9 today. What I realized that, we've done last sample confidence interval. Then you also need to know about small sample confidence interval. In statistical analysis in general, of course, as part of the preliminary exercise, we need to take a sample from a target population. Don't forget, we are limited by budget. We do not have enough resources to study every item in the target population. And let me tell you this. We need to be able to figure out the sample size. What is going to be the number of sample that I'm going to choose in order for me to be able to, figure out, the reason why I go into the population in the first place. Now, I've walked you through, the effect of sample size, when it comes to the weight of the interval. Of course, before now, mathematically speaking, I was able to show that when the sample size increases, okay, the standard error is going to go down and the margin of error, okay, becomes smaller. And not only that, the weight of the confidence interval becomes narrower with a high probability. And what if in a situation, if the sample size is small, when the sample size is small, okay, then you should be expecting the opposite. When the sample size is small and everything stays the same, of course, you expect the standard error to increase, the margin of error to also increase, and of course, that will be characterized by wider range of the confidence interval for the true value of the parameter. But let me tell you this. What determines sample size, particularly if you are conducting a clinical research, let's have biostatistics in mind now. Let's have medical research in mind. What determines the sample size, we got a lot of factors. Okay, methodology, not only that, ethics, not only that, the human and financial resources that you have, determine the sample size. In this class, the other time, I actually walk you through a formula, okay, which we call sample size determination. Now, what is going to happen if I decide to go less than the required sample size? When I say required sample size, maybe you've used a formula, right? Just like what we did the other time. And you Maybe you actually have 600. What happens if you go lower than 600? And what also happen if you go higher than 600? Let me tell you this. The ideal situation is to have a large sample size, but let me also tell you this. It is not also a good idea if your sample size is excessive. I'm going to say this again. Even though when the sample size increases, okay, there's a lot of benefit, right? The benefit in such a way that the standard error will be small, the margin of error will be small. You're actually going to have a narrow width of the interval. But let me also tell you this: there is also what I'm going to call a consequence. When you use an excessive sample size. And before I go into what I want to walk you through today, because we want to talk about sample size, our small sample confidence interval, we got situation where we got no choice than to go with small sample size. And of course, we also got situation where we're going to go with a large sample size. But before I'm going to go into this, in the clinical research, I think I was reading an article published in National Library of Medicine, and I really love the article. Was in 2014 by George Faber and the like. And the title of the article is How Sample Size Influences Research Outcome. How sample size influences research outcome. You can search for that. That was published in 2014 in the National Library of Medicine. Now, I'm going to tell you what was their findings. If you are comparing, let's say, for instance, you are comparing a method with another method. Maybe they've been using a method before on patients, and you now have a new method in place. The old method is going to be called a traditional method. And of course, the proposed method is going to be new method. And maybe you needed to have like minimum of 30 patients in each group. Okay. And we don't just use human being for research. There is going to be an approval. And that is the reason why at times we may got no choice than to settle with a small sample with the one we actually we got. Let's say what the sample size you needed for each group to be able to have statistical power. Statistical power is at least 30 in each group. Okay, maybe you now ended up getting 15, which is going to be a small sample, right? Because in statistical analysis, when the sample size is less than 30, that's a small sample. Okay, now in the end, according to George Faber, the decision was that there was no difference between the traditional method and the new method, even though clinically speaking, there was a significant difference. I'm going to say that again. And the reason why they took that decision is because of the fact that they used small sample. Does that make sense? Which means with a small sample, they were not able to dictate the statistical significant difference between the traditional method and the new method. Now, he went ahead to discuss about what is going to be the effect of using an excessive sample. Excessive sample is not also good. Okay, in a situation where you don't expect to have a significant difference, but because you have used excessive sample, that will signal statistical significant difference. And that is the reason why at times, researchers in medicine, where they may not agree, where they're going to tell you statistical significance is not the same as practical significance. I'm going to say that again. When you use an excessive sample than ideal, that the one required, okay, where you are not supposed to have a difference, okay, then you're actually going to, that will signal a statistical significant difference. And of course, that's going to be a false alarm. We don't want a situation where we're going to waste taxpayers' money because your method indicates, your sample size determination method indicate you should use 50 and you decided to use 100. That's a waste of taxpayers' money. But let me tell you this, just like what I said, we got a situation where we can only tolerate small sample size. And that is the reason why we also need to talk about in a situation where we want to focus on the small sample size, then we're going to have a point estimate, and we're also going to have an interval estimate. But then what I'm going to tell you is, we need to be guided. Whenever we want to choose our sample size, that is a takeaway. We don't just choose sample size. Okay, we got several factors: your method, ethics, available human resources, and financial resources. Does that make sense to everyone? Now I want to go into small sample confidence interval. Now I'm going to focus on the mean, focusing on the difference of means. Let me tell you this. Whenever we're talking about small sample, it does not have anything to do with proportion. Go ahead. Yeah, what I mean by over excessive, how do I know it's over excessive? When I go, like, when I use, what we did last time, right? We got a formula, right? For sample size determination. Let's say we got 600, right? And we decided to use 1000. That is over excessive. Oh, okay. You're talking about the implication, right? Okay, so I'm going to the implication of using I'm going to tell you now the implication of using small sample and the implication of using an excessive sample. For small sample, if, for instance, if you are comparing two different groups, like two different interventions, and maybe it is required that you use at least 30 for each group, and maybe based on human resources or whatever, you only settle for less than 30, 15 and 15, then that may not be able to detect the difference. Even if there's a clinical difference, your decision at the end of the day is going to be, oh, there's no significant difference between the two. Is that not a wrong decision? That's a wrong decision. Okay. Now, for the excessive sample, in a situation where there shouldn't be any difference in the first place between the two interventions, but because you've used so many samples, like excessive sample, okay, that's the excessive sample has a tendency to detect a difference, even if difference does not exist. Does that make sense now? Yeah, and that is why they're going to tell you statistical significance at times does not translate into practical significance. We want an agreement between the clinicians and the statisticians. We want a situation whereby they're gonna, you're working on the same thing, but except that you are taking decision just because you are using different sample size. That's a good question. Now, coming back here now, where we're talking about small sample, the population distribution still need to be normal. I'm going to say that again. For small sample, the population that you are choosing the small sample from still need to be normal, except that the sample is very small. And what is the threshold? The sample size has to be less than 30. And not only that, the population variance or the population standard deviation is unknown. Now, because of that, Z will be replaced by T. You remember the other time, right? Here, we were using T and we were using Z, right? We're no longer going to be using Z anymore. We're going to be using T. And not only that, take a look at this guy. That's a sample standard deviation, okay, because the population standard deviation was not given, okay, and we needed to compute standard deviation from the sample provided. Does that make sense? Then another story here is, okay, the small sample only is applicable to, when the interest is on estimating the mean from one population or the difference of means. This does not apply to proportions. Proportions, with proportion, sample size need to be large. Does that make sense? Okay, now, and this is the the build up. We're not going to be using Z anymore. We're actually going to be using T, right? Okay, now we want to figure out the probability, okay, the probability of T, okay, less than T alpha will be equal to our confidence coefficients. Okay, we're taking a look at this guy now. 1 minus alpha is a confidence coefficient. Okay, and what is my T? Okay, if you take a look at this guy now, I said substituting T into the expression and manipulating resulting inequality. Okay, we're actually going to have this guy. When you take a look at what you see, give me 1 second. I need you to take a look at this guy now. Let me see. Okay. I need you to take a look at this. When you take a look at that guy, I'm only considering the one side. You see minus, right? That's a lower side. When you go back here, when you come back here, what do you see? Say plus or minus, right? Okay. We can consider the lower sided, the upper sided, the two-sided. I just wanted to take note of that guy. And that was why I said that is called a lower confidence bound. The same thing, we consider that for a situation for last sample as well, where we can talk about the lower confidence bound, the lower bound and the upper bound. We can also talk about two-sided. So all what I just needed to see now, take a look at this guy here and take a look at that guy here. You see minus, plus, one is the lower one, the other one is the upper one. Okay, and when you consider the minus and plus simultaneously, the focus is on two-sided. Does that make sense? Okay, so that is what I just want. But let me tell you this. The only difference between this and what we did the other time for the last sample is just that T replace Z and the population standard deviation replace the sample standard deviation. Okay, now I'm going to walk us through an example right now. A manufacturer of gunpowder has developed a new powder which was tested in 8 shells. The resulting muzzle velocities in feet per second were as follows. We got data now. Let me tell you this. If you take a look at this guy now, right, we don't know the population standard deviation. Not only that, this is small sample size. I told you the other time, the threshold as given by central limit theorem, before you can, if somebody say, oh, how large is a large? Oh, how large is a large minimum? It has to be 30. When it is less than that, it's going to be regarded as small sample size. So right now, how many data points do we have? That we got 8 data point, right? Take a look at that. We got 8 data point. Okay. Now we now want to find the 95% confidence interval for the true average velocity. True average velocity, okay, for shells for this type. But let me tell you this. There's going to be an assumption. And that assumption is, okay, the distribution, from where this 8 we're choosing from has to be normal. That is the assumption. If it is not normal, we can't use parametric method. When I say parametric method, the parametric method is the method we've been doing. We've been like using a T, using a Z. That's a parametric. The parametric actually rely on assumption of normality. We have other side of statistics where if the assumptions of normality is violated, right? If the assumptions of normality is violated, we can actually resort to non-parametric. We got non-parametric, okay? Now, we now want to use this approach now. The Y bar, we're going to compute the sample mean. Okay, we're going to get a sample standard deviation. Now, when we got, because we got 8, right? The sample mean is this guy, 2959. You're going to sum the 8 together, divide by 8, right? You get 2959. Then you compute the standard deviation. Okay, you can use your calculator. The standard deviation will give you 39.1. Don't forget, the standard deviation you're going to find here is going to be sample 1. And don't forget, we got 2 estimator for variance. You know the one you're going to use? If I want to get the sample standard deviation, I will first compute the sample variance. And don't forget, the sample variance, the one we're going to use, the estimator we're going to use is the unbiased one, the one that is divided by sample size minus 1. Does that make sense? Okay, now, why do I have a square root of 8? Because the sample size is 8. Now, I need to do something here where I'm actually going to go, I need to figure out what is the T value. The other time when we're working with the last sample interval, we're focusing on the Z value, where we're going to go into statistical table to figure that guy out, or we can make use of our software to figure out the values of Z. But right now, we're actually going into statistical table. We're going to check on the T. There's a T, and that very T is actually going to come with the degree of freedom. The degree of freedom here is just going to be the sample size minus 1. That's why you see we got 8 minus 1. That's going to be 7. If you go to the textbook we're using, okay, if you go to appendix 3, table 5, okay, on the recommended textbook, okay, where when you check for that, this is what you're going to have. Okay, the alpha divided by 2. Don't forget, the 95% is 1 minus alpha. Okay, alpha itself is going to be 5%, 0.05. If I divide 0.05 by 2, that will be 0.025. So which means I actually need to go to the statistical table, specifically T table. I'm actually going to check 0.025 under the degree of freedom 7, and that will give me 2.365. Okay, now I'm going to plug that guy in here. When I do that, okay, the whole of this guy now becomes my margin of error. If you take a look at this guy here, the 32.7, it's actually the margin of error that will be subtracted from the point estimate and also going to be added to the point estimate. And at the end of the day, we can conclude that the true value of the average velocity will actually lies in the interval. Any question? Any question? Okay, so you said I should clarify why we use t-distribution again, right? We use t-distribution because number one, the sample size is small, and number two, the population standard deviation was not given, is unknown. There are two reasons to use t. Okay, two reasons to use t. And we use t for small sample, right? When the sample size is less than 30, not only that, the population standard deviation is unknown. That's a good question. Very good question. Okay, now I'm gonna go into the next. We're done with the one population now, and I want us to look at situation where we're going to be focusing on two populations, or like focusing on two groups. Maybe I want to compare the average, okay, in two groups. It could be economic average, it could be clinical average, and so on like that, depending on where you actually conducting your research. Now, y bar 1, y bar 2 is actually the sample means, okay, that we obtain, okay, from, we actually compute that from the sample. Don't forget, the estimator is the sample mean, okay? Now, if you take a look at this guy, okay, for large sample size, the pivotal quantity is actually going to be Z. You remember when I say pivotal quantity here, you're actually going to see that the difference between the sample mean difference and the population mean difference divided by population, the standard deviation of the difference. We've done that before. Why is it Z? Okay, Z for large sample. Z for large sample. But let me tell you this. We have so many assumptions. We're working with two populations. We could have a situation where, the two variances, the population variances are known. If the population variances are known, the population variance for this and this they are known, I can go with Z. Okay? Irrespective of the sample size. But provided the population that we choose the sample size from, respective sample size from, is normally distributed. Okay? But what if in a situation where the population variances are unknown, we don't know the population variance, okay, and they are assumed to be equal. Look at this. The sigma 1 square equal to sigma 2 square equal to sigma squared. Of course, I'm actually going to have this guy now, right? That's what I'm going to have when I plug in sigma squared in place of sigma 1 squared, sigma 2 squared, and I try to find the square root of that. I'm actually going to have that guy. Now, in this situation now, okay, then we need the idea of a pooled variance. Pooled variance. Okay, the idea of a pool variance is going to come in when the variances of the populations are assumed to be the same. Now, and that is what you're going to see here, okay, that I want to talk about, pool variance. Now, I know before you've seen this guy, right? And you're going to be wondering, why is it that, what led to that? What led to that is this guy. Because if you look at the sample variance for each group, it's going to be summation. It's going to be the square of the sum of the deviation divided by n minus 1. For this group, the other group is also going to be n minus 1. If I use n1 for this group and I use n2 for the second group, when I have n1 minus 1 plus N2 minus 1, that will give you N1 plus N2 minus 2. We're pulling the variance. And you know what? Because of the fact that, take a look at this guy, sample variance, the unbiased one is summation, okay, y minus y bar squared, okay, y minus y bar squared divided by n minus 1, okay, then I can say this guy here is the same as n minus 1 times s squared. Isn't it? That was what led to the other one. You remember the unbiased sample variance, where you have the summation y minus y bar squared divided by n minus 1. If I want to make summation y minus y bar all squared the subject of the formula, the n minus 1 is going to multiply the s squared. If I do that for each group, that is what led to that guy there. And don't forget the other time we proved that this was unbiased, right? We proved that this was unbiased. Now, if that is what you have now, I needed to take note of this guy. If I have a W, okay, you know, some of you may be wondering, what led to this? For the first group, let me give you the one for the first group. Have you seen this before? N minus 1 sample variance divided by population variance. If you go to chapter 6 or something, that will be distributed chi-squared. Chi-squared is a ratio of sample variance to population variance multiplied by the degree of freedom. What am I doing here? I'm doing that for two populations. Instead of n minus 1, what am I having? This is for, you know, this guy here is n1 minus 1 plus n2 minus 1. You know that? N1, like adding the degree of freedom for the two group. Adding the degree of freedom for the two groups is going to give you n1 plus n2 minus 2. Then what will now be the sample variance? Oh my God. The sample variance is going to be a pooled variance, because I'm talking about two groups. And the population variance is going to remain the same, sigma squared. Take a look at that. Okay. Now, and don't also forget what led to this guy. If you take a look at this guy, this is what led to that, right? I can at the same time, I can write that guy as that. I'm putting into consideration the pool variance now. If you take a look at the connection between the two. Okay. Now, what am I driving at? Okay, this is what I'm driving at. How do we form a t-test? There's a difference between t-distribution and a t-test. I'm going to say that again. There is a difference between a t-distribution and a t-test. There's a difference between a z-test, okay, and normal distribution. There's a difference between f-test and f-distribution. Okay, if I want to conduct a t-test, then I need a t-distribution. The t-distribution is actually going to be the distribution of the non-hypothesis. It's just like somebody commit an offense in the state of Minnesota, that person will be tried using the Minnesota law. Okay, the Minnesota become a territorial jurisdiction, like a distribution. Does that make sense? If you try if that person run to California and that very guy was actually tried in California, oh my God, the California does not have a territorial jurisdiction, which means you are using a wrong distribution, okay, for a particular test. Okay, now, because we want to talk about t-test, right? Because we need t. You know, the other time when the sample size is large, the pivotal quantity was Z. Now, what we want to do now, how do we derive pivotal quantity T? Because that is what we need here for small sample size. This is the origin. If you look at what you've done in star 4101, T distribution is a ratio of, if you take a look at Z follow normal distribution with the mean 0 and variance 1. W follow a chi-squared. Okay, W follow chi-squared with V degree of freedom. That W is this guy here. That's a chi-squared. This follow chi-square distribution. Okay, W follow chi-square distribution. So we're trying to remind you the origin of a T test that you call test statistic for T. It is the ratio of Z, okay, which is Z is a standard normal random variable divided by the square root. The W is a chi-square, follow chi-square distribution with V degree of freedom. Now, take a look at this guy. Where is it coming from? Oh my God, that's a Z, right? How do I know that? Come back here. You got to see now. Do you see that Z, right? When we assume that we have said that a sigma 1 square equal to sigma 2 square, we have that. I want to plug in this guy now in place, and that is what you actually see here. Then divided by square roots. What is the W? What is the W? What is the W? I'm gonna come back. Okay, this is the W. You see that? That is the W. Then what is V? V is the degree of freedom for two groups. The degree of freedom is going to be N1 plus N2 minus 2. Is there anyone who doesn't understand how we got here? What are we doing now? We're deriving pivotal quantity for T. The pivotal quantity for T is the ratio of Z to the square root of W divided by V. Z follow standard normal distribution. W follow chi-square distribution with V degree of freedom. And the degree of freedom here is going to be N1 plus N2 minus 2. Now, when I simplify that guy, oh my God, simplify that will lead us to this, which is a formula we use in applied statistics today. If you want to test if there's a significant difference between means from two groups, when the population variance is not given and they are assumed to be equal, you can see the pool. Okay, so take a look at that. Now, having known this guy now, with the pivotal quality now, do you know I can actually construct a confidence interval now? Oh my God, I can construct a confidence interval now for the difference of means where the sample size from each group is small. So what are we talking about? What am I plugging in? Take a look at this guy. It's what I'm going to use here, right? Look at that. That's what I'm plugging in. Because if you want to talk about what is going to appear after the T, it has to be standard error. But the standard error here now reflects the pool standard deviation. Take a look at that. Okay. Now, if I want to check for T in the T table under the degree of freedom, because I'm working with the two groups, don't forget the degree of freedom now is going to be this guy. The sample size, first one plus the second one minus 2. But when I was working with the one population, the degree of freedom was just sample size minus 1. Does that make sense? Okay, so I'm going to walk you through an example now. Now, without wasting your time, we want to compare to reach maximum efficiency in performing an assembly operation in a manufacturing plant. New employees require approximately 1 month training period. A new method of training was suggested, which means They want to compare new method with the conventional method, which means they got two groups, right? Okay, now was suggested and a test was conducted to compare the new method with a standard procedure. Two groups of 9 new employees each were trained for a period of 3 weeks. One group using the new method and the other following the standard training procedure, and the length of time in minutes is actually that. You can see now, standard, new, and these are small sample, right? They are small sample, right? Okay, now we actually want to construct a confidence interval. You know, we actually want to see where the true difference is going to lies in the interval with the associated degree of confidence. Let me tell you, if I want to know whether there's a significant difference, okay, between two means, I can construct confidence interval. Or what I'm just going to be looking for. If the confidence interval is from negative to positive, then there's no statistical difference because zero lies in the interval. When zero lies in the interval, you know what it indicates? There's no statistical difference. Okay, but if there is no zero in the interval, if you are from positive to positive or from negative to negative, that indicates statistical significance. Now let's take a look at this guy now. Okay, you're going to compute the mean of the first one, the mean of the second one, the sample standard deviation, and the standard of the other one. Take a look. That is what I'm actually doing here. You see all of that? Then we're going to compute the sample, the pool variance and the pool standard deviation. And don't also forget, we need to get the degree of freedom, which is going to be the sample size N1 plus N2 minus 2. Okay, that gives us 16. Then don't forget, you're going to go to the table, you're going to check. By the time you plug all of that in, this is what I got. Is there anyone who have a trouble time understanding how the computation is done? Is there anyone? Is there anyone? Now, if I really want to know whether this is significant or not, if I do 3.66 minus 4.71, that would be negative. If I add, so which means the lower bound is going to be negative, the upper bound is positive, and that means there's going to be zero in the interval. When you have a zero in the interval, of course, you're always going to have zero between negative and positive. What does that indicate? There is no statistical significant difference between the two methods because the zero lies in the interval. Does that make sense? Okay. Now, this is a summary of what I just walked you through. That is a summary. Please take note of that. Now, lastly, before I go, I told you the other time, population parameter could be mean, it could be variance. We've been focusing on mean, proportion. We can also conduct a statistical inference on variance. So now, the confidence interval for variance can also be done as well. You know, I told you the other time. Okay. That divided by that is the same thing as that guy. And the whole of that guy follow a chi-square distribution. Which means if I want to figure out a p-value or I want to get a critical value, then I need to go into chi-square table for variance. Okay, so what do I want to find? I want to find the probability of that line between the lower bound and the upper bound for variance. And this is going to translate to this guy, okay, equal to the coefficient, okay? Then, now what is the formula? This is the formula that we're actually going to use. If you want to get a confidence interval for variance, that is going to be the lower part. That is going to be, you know what, all what you just need here is to plug in, what is your sample size? What is your sample variance? Then we're going to check for those values in the table. We're going to check it from the chi-square table. I need you to pay attention to this. You see alpha over 2 from chi-squared, but this is 1 minus alpha over 2 from chi-squared. Okay, take note of that. The same thing is applicable for standard deviation. Let's say, for instance, you want to conduct and construct confidence interval for standard deviation, it's not going to, where you have a squared, maybe standard deviation. Now take a look at this. Let's go to question. You have this question. An experimenter want to check the variability of measurement. Variability, that's variance of measurement obtained by using equipment designed to measure the volume of audio source. And you are given the observation. They want you to estimate the sigma squared. Why do we say estimate the sigma squared? Because 1,000 investigator, when they choose a different, I mean, the same sample size, because they were choosing at random, they're going to have different value for variance. Now, estimate sigma squared with the confidence interval 0.90. Okay, now compute your sample variance from the data, get alpha over 2. Okay, get the degree of freedom. Okay, we're going to check from the chi-square table. Okay, now we check it from the chi-square table for alpha over 2. And we check it for chi-square table for 1 minus alpha over 2 for the degree of freedom, 2. Okay, now I need you to take note. The one here will be always greater than the one here. I'm talking about the denominator. And that is why in the end, they're going to have the same numerator, but different denominator. Because you're going to check for alpha over 2 with the degree of freedom and 1 minus alpha over 2 with the degree of freedom. At the end of the day, this is what I have. Okay, this is what I have. Okay, when you are dealing with the variance, we are trying to tell the world the true variance, the true values of the variance will lie between 3.53 and 205.24. And that was why I said, notice that this interval for sigma square is very wide. Okay, primarily because n is quite small. In a situation where n is large, what do you expect? Narrow interval when the sample size is large. Any question? Any question? What of in a situation where I want to compare variances from two groups? For the variances from two groups, I'm not going to do difference of variance. You know, we normally do difference of means, right? Mu1 minus mu2, but I'm going to do the ratio of the variances. And the ratio of the variances will follow another distribution. I want to award an extra credit now. Can somebody tell me what distribution in statistics is the ratio of the variances we follow? Extra credit. Can somebody tell me? Go ahead. Oh my God, good job. I'm giving you 2 points for extra credit. Send me a message. You could add that to your midterm. So the ratio of variances will follow F distribution. Okay? And the reason why it follow F distribution, you know why? Because when you are conducting inference on variance, it follow chi-squared. And F distribution is the ratio of two independent chi-squared. That is the reason. That's why I'm going to stop today. Check for your results for the midterm 1 tomorrow, or probably before the end of the day tomorrow. Go ahead. How do I do what? Oh, how do I feel about it? I think it's looking promising based on what I've graded so far. It's looking promising. But don't forget, we live in a stochastic world. Anything can still happen. Like I've graded like 50% of the class. Okay, so but I'm hoping it should be fine. Okay, make sure you stay safe and have a lovely day. Bye for now, everyone.